In Chapter 4 of the workshop, you'll become familiar with interrupts and the timer. You'll use the timer to generate interrupts to the main routine. If you're not already familiar with the concept of microcontroller interrupts and interrupt service routines, now would be a good time to look up that topic online. The Tiva C-Series Nested Vectored Interrupt Controller, or NVIC, is tightly coupled to the central processing unit. It handles all of the exceptions and interrupts that come into the CPU. There are 8 programmable priority levels and priority grouping. In most microcontroller interrupt vector tables, the priority levels for each peripheral are set by the manufacturer, and you have no input into what they are. That's not the case on this device. You can reprogram the priorities as you like. This device has 7 system-level exceptions and 65 peripheral interrupts. It has automatic state save and restoration for entering and exiting interrupt service routines, as well as automatic reading of the vector table entry to quickly facilitate this process. One of the first rules that you learn when programming interrupts on a microcontroller is to not nest interrupts. But sometimes you need to nest interrupts. For instance, you need to get a very low latency motor control or device quickly taken care of. You need to get to it quickly, and you have other interrupts that take too long. Those long interrupt service routines will need to be interruptible. On most microcontrollers, you'll have to program this tedious process in software. On the Tiva C-Series devices, you can do it by programming the NVIC hardware. You can make interrupts preemptive, and you can nest them. Interrupts can also be tail-chained, which is something I'll explain more in the next few slides. Interrupts are deterministic. They're always either 12 cycles or 6 cycles if they're tail-chained. Taking a look at the diagram at the bottom, we can see that this is an application with 2 interrupts. From the left to the right, the first interrupt that goes off is for motor control. Motor control requires extremely low latency. You can't wait. You must act on the interrupt quickly. The second interrupt is a repeat of the first. In the third instance, a communication interrupt, like the CAN, has started operation. Communication interrupts usually involve FIFOs and buffers, so they can wait. When the motor control interrupt arrives, we can't wait for the communications ISR to complete. The motor control ISR must preempt it. The remaining instances are further example. Remember that the nesting behavior is programmed into the NVIC hardware. Tail chaining reduces interrupt latency. In this diagram, 2 interrupts go off at the same time, IRQ1, which is the higher priority, and IRQ2. In a typical processor, the state of the processor would be pushed onto the stack. The highest priority interrupt service routine would run. The state of the processor would be popped off the stack. At this point, the interrupt controller would detect that there was another interrupt pending and repeat the process for the lower priority interrupt. Note that the pop and the push right in the middle there are doing the exact same thing but in opposite directions. There's really no need to do those. Cortex M4 interrupt handling is done in hardware. We have a very short push at the beginning, and then we see that ISR1 runs. The NVIC detects that another interrupt is pending. It simply transfers execution to the pending interrupt's ISR. This process takes 6 cycles. When the second ISR completes and no other interrupts are pending, the state of the processor is restored. This will result in a significant decrease in interrupt latency in the typical interrupt-driven system. The next NVIC operation we'll look at is called preemption. The NVIC allows preemption of the pop or push process. In the diagram, we can see that a second interrupt was detected while the interrupt controller was restoring the processor state from the first interrupt. The typical processor is unable to do anything about the situation. It continues its pop process. It then pushes the state of the processor for the second interrupt, resulting in many CPU cycles being wasted. On the Cortex M4 NVIC, the second interrupt will preempt the pop process and trigger a tail chaining event, again decreasing interrupt latency. The next NVIC issue to look at is late arrival. In this case, the lower priority interrupt, IRQ2, goes off just before the higher priority interrupt. In a typical processor, it would be pushing the status of the processor for IRQ2. As soon as it detected that there was a higher priority interrupt, it would finish the push, start a second push, and then go through the entire normal sequence. The cycles required to perform the extra push operation are completely wasted. In the Cortex-M4, the NVIC will detect that a higher priority interrupt has occurred. It will simply transfer execution to ISR1 instead of ISR2, and then run ISR1. At the end of the interrupt service routine, it will then tail chain into ISR2. Again, a significant savings in terms of interrupt latency. Cortex-M4 interrupt handling is totally automatic. There's no instruction overhead. On entry, the device automatically pushes registers R0 through R3, R12, the LR, the PSR, and the program counter onto the stack. In parallel, the address of the applicable interrupt service routine is prefetched onto the instruction bus. The ISR is then ready to start execution as soon as the last stack push is complete. On the exit side, the processor state is automatically restored from the stack. In parallel, the address of the interrupted instruction is prefetched, ready for execution upon completion of the final stack pop. Exception types on the Cortex-M4 include reset, the non-maskable interrupt, hard fault, and the 7 shown in the table. Note that the priority levels for the reset, NMI, and hard faults cannot be changed. A hard fault is all classes of fault when the corresponding fault handler can't be activated because it is currently disabled and masked by the exception masking. A memory management fault is caused by a memory protection unit violation or an invalid access, such as an instruction fetch from a non-executable region. Bus faults are an error response received from the bus system caused by an instruction prefetch abort or a data access error. Usage faults are caused by invalid instructions or invalid state transition attempts. SV call is a system service call via the SVC instruction. Note that the priority is programmable for most of these faults. After reset, the Cortex-M4 vector table is located at address 0. Each entry in the vector table contains the address of the handler or ISR to be executed. If you look down at the bottom at the initial stack pointer value, that value at address 00 is used as a starting address of the main stack pointer. It's typical to relocate the vector table after bootloading the device, and this can be done by writing to the vtable register. The vector table must be aligned on a 1K byte boundary. If you like, open up Startup under ccs.c in Code Composer for a complete view of the vector table. The General Purpose Timer Module, or GPTM, has 6 16 or 32-bit and 6 32 or 64-bit general purpose timers. They can be used for capture, compare, or pulse width modulation. There are 5 different time modes available: one-shot, periodic, input edge count or time capture, PWM generation, and real-time clock. The timers can count up or down. PWM generation is simple with no deadband generation and software inversion of the outputs. The module supports synchronization across multiple timers, daisy chaining, and user-enabled stalling during debugging. This last feature stalls the timers during debug when the user clicks the halt button and prevents unwanted timer interrupts from occurring. The timers can also trigger the ADC sample sequencer or DMA transfers. In Lab 4, we'll use the general purpose timer to count down from a preset value. When the timer reaches 0, an interrupt will be generated and the timer will be reloaded. The NVIC on the timer C-series device will then find the correct address of the interrupt service routine you've written and execute it. These are all real-world skills that you'll need over and over again when working with any microcontroller.